Thanks for bearing with us today, everyone. I know it's the end of the day. Hopefully this will be the coolest talk of the day, but we'll see. Don't count your chickens before they hatch, I guess. So yes, I work for Space Operations New Zealand. I'm a space operations engineer. Basically, what that means is I run around like a headless chicken, doing just about everything there is to do there. But it's good fun. It's good fun. When we're not busy tearing our hair out, we think we're enjoying it. So for those of you who might not be aware or who didn't see Robin's talk earlier today at the start, the keynote, we own and operate a satellite ground station about halfway between here and Bluff. We have, and I'll come to this a bit more later, but there's obviously satellites going over the top of us all the time, and somehow those satellites need to talk back down to Earth. So we essentially act as an internet provider for spacecraft. We provide the link between the space and the ground, and if you don't have that link, then your spacecraft is about as useful as a flying brick, but actually it's less useful because you can't use it to build a house, and it's a lot more expensive. So, obviously this is a Python conference, it's not a space conference. So, what do we do with Python? Well, we do use Python. What exactly are the benefits of using Python in space? So, obviously it's got very fast turnaround time. This is very similar to using Python anywhere. You've got a very good modular structure, and I'll come back to why that's important in a moment. And you have very strong community support. So there's lots and lots of good libraries out there, both community libraries, third-party libraries, and also built-in libraries. And that's really, really useful. I'll come back to why that is so critical for us in a moment. However, it's not all sunshine and rainbows. So some things just to be aware of with Python is that obviously being an interpreted language, it is slower to run than a compiled language. So anywhere that you need higher performance, you might be better off looking at something that's a bit more low level, like C or Rust, or one of those more one of those compiled languages. It's also not very well optimized generally for things like this little bad boy. This is a Raspberry Pi Nano. This is a little microcontroller. You can get other similar microcontrollers like Arduinos, and all sorts of things like that. They don't run a emulator very well, so they don't run normal Python. You can use MicroPython, but again, sometimes you might just be better off looking at one of the languages designed for low-level computing, such as Rust or C. So what's the solution here? Basically, it's to take a compromise of using Python for your high-level development or for any data processing you do. So that's the things that Python's really good at. So we'll use the right tool for the job, but also using something different for your low-level sources, low-level software, or anything that you need high performance on. So again, just using the right tool for the job, it's the same as anything really. So coming back to what we do. So we're based here in Invercargill, halfway between here and Bluff technically is our ground station. But this is a very, very rough diagram. If you saw Robin's presentation this morning, he had a much more accurate diagram of what's sort of going on. But this is very roughly anywhere in that circle, any satellites within that circle we can communicate with. So obviously the Earth is round, which means so as satellites go away from us, they drop below the horizon and we can't see them anymore. That leads to the circle of range. It's essentially antenna coverage. And if we have for example, a spacecraft that flies through there, it would look something like that. Again, it's a very rough diagram. Basically, again, anytime that the spacecraft is within that blue circle, we can communicate with it. When we're communicating with it, we can download data. When we're downloading data, we can charge our customers for that data. So we're making money. So we really, really want to have the most amount of time in that circle. How can we improve the amount of time in the circle? We can add a second ground station. New Zealand's a very long country. If we add one at the top and we have one at the south, we can get approximately 50% more coverage time on that spacecraft. So just a little bit of perspective, a pass normally lasts around 8 to 12 minutes. So if we have a second station rather, we can get about another 4 to 10 minutes of pass time. 4 to 6 minutes of pass time per pass that we can be downloading data. That's more money that we can get. That's from an economics point of view, of course. From an engineering point of view, there could be lots of satellites. They can be going all different ways. We have multiple spacecraft that we're trying to track. We also have multiple ground stations that we're trying to track them from now. This leads us to a problem. We still only have a limited number of ground stations, and there's lots of spacecraft in space. Which ground stations do we use to track which spacecraft? We can only track as many spacecraft as we have ground stations. We can't track them all. Which stations do we use and when? This is a multiple input, multiple output problem, and it turns out to be quite tricky to solve. In fact, there's a lot of research in the industry that's going into this right now, and we are trying to do our bit as well to develop our own system to develop a schedule of tracking as many satellites as we can, really cramming them in and making the best use of our antennas and making the most money we can out of all that. But like I say, it's really difficult. That's all research that I'm doing through the University of Canterbury at the moment. And we're looking at producing that schedule I mentioned using Python, funnily enough. However, if we take a sort of a step forward, normally talk about step back, let's take a step forward and look a bit closer at the problem. Let's assume that the schedule has been determined already. And we're going to look at a single antenna. So the single antenna now has a schedule already. We know which spacecraft we're going to be tracking with that antenna at which point in time. That's a much simpler problem to solve because it's a single input, single output. You have one antenna, one spacecraft at one point in time. I say it's much simpler. That does not mean it's much easier. So the issue is there's still a lot of technical requirements you need for your scheduling system. So you still need to be accurate with timing. You need to be accurate with positioning. You need to accurately point the antenna at the spacecraft at the right time as it's going over and keep it within that track. Some antennas require fractions of a degree, like you're talking hundredths or thousandths of a degree of accuracy on these antennas, on these spacecraft. Otherwise, you just won't pick up the signal. So the other really important thing I mentioned earlier is Python's inherent modularity. How does that help us? So we have multiple different antenna types. So you can sort of see here on the bottom left, there's two different types of antenna. We have a Yagi antenna on the far left, and on the second left is a satellite dish or a parabolic dish antenna. So those are similar to, on your house, you might have one of those pointy, sticky aerials, and that's for terrestrial TV. So anywhere the TV is being broadcast from, say, a hilltop or something. Then you might have a sky dish antenna, which is where the signal is being picked up from a satellite. It's a very similar concept to what we use, except our antenna is just a bit bigger and they move. The other thing we have is, so there's different antenna types that we have, and each of these antennas have different accuracy requirements. As I mentioned before, some of the antennas have fractions of a degree worth of accuracy that you need to achieve. But some of them, like this one on the far left, the Yagi antenna, that's got a beam width of 15 degrees. So as long as you're within that 15 degrees, you can track your satellite quite happily. Ideally, that would be within plus or minus 1 degree, but you can get away with up to about 15 degrees. For a 30-meter antenna, and those of you who are here this morning, again, Robin mentioned that we had a 30-meter antenna now that we are leasing up in Warkworth. That is one of these really accurate antennas that you require a sub-degree accuracy. Otherwise, you just do not pick up your signal. So these really, really strong differences in requirements obviously mean that we need a system that can handle having these different requirements. It has to be able to handle all of them. The other thing to consider is we have lots of different types of hardware as well. So we also have radios that we've got to be able to talk to and control. We have web accessible relays, web controlled relays that we also have to be able to control using the same scheduling system, and we have to synchronize all these to be able to control the antenna properly. With Python's really modular approach, it makes it's super easy. So I'm not sure if I don't talk about this further in, I don't think. I forget, sorry, I wrote the speech last night. So with Python's modular approach, we can essentially break up all of these different control systems into Python classes. So we have a Python class, a control class for each of these different submodules, or subsystems rather. And all the differences are handled by those subclasses, and then we can bring those all together with a common interface to the central control system. So that central control system only has to support one interface, and it just makes it so much easier. You can plug and play. If you're controlling one type of antenna and you go to a different type of antenna, all you do is you swap out the control system for the first antenna type with a control module for the second antenna type, and it just works. It's magic. And Python is really, really useful for that because, as I say, its inherent inbuilt modularity just works. It lends itself perfectly to those requirements. So we also use lots of external libraries. I mentioned this before. Internal and external libraries. Some of the external libraries that you provide, or the third-party libraries, we should probably say, things like the requests module, the Python requests module, the Python date util module for parsing date times. These sorts of things we use for a lot of our web processing. So we have a lot of web interfaces. So both our antennas themselves are controlled through web interfaces because we find that is a really quick and easy way to develop an interface for the antenna. It's really convenient to use. It's very versatile. But the other thing is when you're actually tracking spacecraft, how do you know where to point the antenna? So you can download, anyone can go online, you can go to spacetrack.org, I believe the URL is, sign up to an account. That's a site run by the US military. I think it might be administered by Space Force now, I don't know. But they track everything in space. They have big radar antennas and they track all objects in space, and then they compile a list of everything and release it publicly, open source to anyone with an account. So you can sign up for free. You can, if you don't want to sign up to the SpaceTrack site, you can go to another site called Celesttrack, and they're an open source, open source way to download the data of spacecraft. So it's really easy to get your hands on this data of where spacecraft are. This data is called a TLE, a two-line element, and it looks a bit like that. Super simple, right? That's all good and well, except somehow we've got to turn those numbers into where do we point our antenna at this point in time. That's a lot harder. So behind the scenes of those two lines, technically three lines because you got to name the spacecraft at the top, there's a whole load of computation. There's a big computational model, a quite hairy algorithm which we don't really want to compute. Fortunately, there are Python modules, third-party Python modules that will do all of that for us. They'll do all of that heavy lifting. So we just use those to turn a TLE, a two-line element, bits of various numbers in a particular format, into something that looks a little bit like that. So in particular, we use AstroPy and Skyfield as listed there. They're quite common in the industry, I believe, for Python. Anyone doing astroastronomy uses them as well, I understand. But on top of that, we then, once we have the model of where to point the spacecraft, we use other libraries to interface with our hardware. So things like PyModBus to interface with any Modbus protocol systems, PySerial to interface over a serial link with any of our controllers or control boards. So that's similar to USB or RS-232. Obviously ZMQ as well, we use ZMQ. It's a networking protocol which we use for streaming data. So any radio signals we can just stream over the network using ZMQ, which is really convenient. I'll come back to that again in a few slides. We also do a lot of signal processing and data analysis, and also data visualization, which I'll come to. And for that, we use obviously NumPy and SciPy, the standards in the industry, and also Matplotlib to present the data, as well as GNU Radio to actually receive and process the signals. And I'll come back to GNU Radio in a bit. Obviously, we use lots of inbuilt libraries as well. I'm not going to go through them all. I'm sure most of these libraries are very familiar to a lot of you. We use SQLite as our database engine, and we use JSON heavily in our web interfaces, for example. But they're all standard. Obviously, they're all inbuilt, and it's super easy if you try and develop code to just go, oh, I need to open this CSV file. I'll just import the CSV label. I don't need to go and download it. I just import it from the built-in library. So we've talked a lot about Python so far. Heading back to the technical side a little bit. What is a radio? what do we do? So this is all leading up to what is GNU radio, and I'll come to that. But essentially, a radio consists of an antenna. You have to have an antenna to pick up the signal. That's what turns the radio electromagnetic wave, essentially a light wave, which is traveling through the air, into an electrical signal that you can actually detect and do useful stuff with. But this is still a very, very, very small signal. Like, you're talking, if I was standing here, and I don't know who's it first, but you right in the corner over there, if I was whispering, and I'd have to turn my mic off for this to work, if I was whispering, do you think you could hear me? No. These antennas have signals of about that sort of comparable strength from me talking compared to me whispering. So we want to hear me talking because we can do stuff, we can hear that with our ears, we can understand it. But me whispering is not going to be so understandable for my friend sitting over there in the corner. So we need to amplify that signal. We need to increase the strength of the signals we receive. And so for that we use an amplifier and also RF filters and a bunch of other technical stuff. So we need to first of all boost that signal. Now that we've boosted the signal, we can start doing useful things with it. So for example, in a car radio, classic example, or maybe you've got a desktop radio, an alarm clock radio, for example. Most of those, especially older models, will be entirely analog. So they have a whole bunch of capacitors and resistors and inductors and all sorts of funky stuff inside of them. Not silicon chips, quartz crystals and all that sort of stuff, doing lots of cool things. But it's entirely analog. And once you put it in the radio, it's very hard to change it. So you sort of have one radio set up. Well, you build one radio, and then that's the radio you have forever, pretty much. But the output for that then can go to something useful like a speaker, and you can listen to your music. But all this analog signal processing in the middle here, basically that is taking your radio signal, which is now an electrical waveform, and converting that from an electrical waveform into a sound wave, or a sound waveform. So that's similar to if you had AM or FM and you switch between AM or FM on your car radio. That's sort of what that is doing. That is demodulating the signal from the radio waves into an audio wave. The new big thing in radios, though, we're not interested in analog. Like I said, analog signals, analog radios are very difficult to change. But in a fast-paced space environment like us, we need to be able to rapidly change how our radios work because we have different customers with very different needs for their radios. So where we go to there is something called a software-defined radio. So essentially, it's all the same front end. So you still got the antenna, you still got the amplifier, but then instead of going into your analog circuitry, instead of having all of that demodulating and AM to audio in an analog hardware setting, you just put it straight into a digitizer. So this is a device which basically it measures the voltage signal coming in and it turns it straight into ones and zeros. And the ones and zeros that come out, you can feed those into some signal processing software on the computer. Essentially, those ones and zeros just represent a voltage amount, the amplitude of the signal coming in. So then once you get to the computer, you just have a signal. You've got data that you can just process. And you can, again, use your built-in libraries, your third-party libraries, and you can use other systems such as GNU Radio, which I'll come to on the next slide, I believe, to understand that data and to do the same as what you would with the analog. But now we can do so much more because we can save it directly. We could send it out to a speaker like we were originally doing, or we can even stream it directly over the internet to someone on the other side of the world who's looking at a screen trying to fly a spacecraft. So it's something that becomes very useful. So this is GNU Radio. I've been talking about this. What actually is it? This is a framework which allows us to design our radio characteristics. So it's very simple to use. You drag and drop from this library, essentially, of blocks or functions, if you will. So you might have one, actually I'll go through them in a moment. So you might have a bunch that act as variables. They store parameters. So that might be whether you're using an AM or an FM radio, it might be the frequency the radio is tuned to. You have input blocks. So that's how you actually get your data out of your radio and into this flow graph. You might have other filters and analog, well, essentially not modulating, simulating the analog hardware in your analog radio. All that stuff would be represented by blocks in this flow graph. And finally, you can output the data. And as I was saying, you can do all sorts of stuff. You can output in whatever way you want. These particular two are outputting to a live stream, essentially live video output that an operator can look at and understand what's going on. And it also outputs to a ZMQ socket, which can stream again across the network to anywhere in the world. These things can get quite complicated. So why use GNU Radio? Well, coming back a little bit to the whole Python side of this conference, if you don't have, so remember those blocks that I showed you that you can drag and drop? There's also only a limited library there. If there's not one, it's a very big library, but if there's not one that you want, or if you want custom systems, custom signal processing, you can write your own. And you can do that using Python. You can also do that using C or C++. So if you're wanting really fast development, again, you could go with Python. But sometimes you might need some faster, higher speed processing that you can go down to C++. It has fantastic support for Python. So GNU Radio has been written by people who clearly are Python geeks like the rest of us. It's all written in C++, I believe, but the support for Python is just unbelievable. You can you install GNU Radio, and then that, I think, also installs the GNU Radio module into your Python environment automatically. And then you just import that module, and you can call any of the blocks. So those flow graphs I was showing, you don't have to run it in the GNU Radio terminal. You can run it from Python by simply calling the block as if it was a function. It's super easy to do and super convenient. And finally, so GNU Radio is supported by all major OSs, as you'd expect. A little bit of trouble installing on Windows sometimes, but it works very well on Linux. And as with all good software, it's open source. So it's got a fantastic community behind it again, as most open source projects do these days. And the documentation has just gotten better and better. The support for different radio front ends has gotten better and better and more convenient to use. So it's a super quick and easy tool to develop even the most complex of radio systems. And I will be around all weekend rather, and I'll try over the next couple of days to bring in a Wii software-defined radio, and I can do a demonstration of GNU Radio for anyone who wants to. So if you want a demonstration, by all means, come and hit me up throughout the rest of the conference, and I'm more than happy to give it a bit of a show-off. There's many other reasons to use GNU Radio, but this is a Python conference, not a GNU Radio conference, which they definitely exist, by the way. I might skip over the rest of the reasons, but by all means, just bear in mind that, so this is a tool that we can use. GNU Radio is a tool that we can use to basically do all of our radio processing and all of our signal processing. What else do we do? So we have a large R&D program at SpaceOps. We do a lot of work with visualizing signals, and I'll come back to why that is so important for us later and what we can determine from signal visualization. However, we also do a lot of, Robin sort of mentioned earlier briefly that we try and find spacecraft. So when someone launches a spacecraft, you don't immediately know which one's yours. Often they'll launch in a group. So you'll have 5, 10, 50 spacecraft operators will do what's called a ride share, and they put all their spacecraft into one rocket. And when they all get released, they get released in a big stream. Some of you will have seen the SpaceX or the Starlink trains, I think they call them, which is the long train of spacecraft going over 1, 2, 3 at night. Those are an example of spacecraft that will get released at once, and they come out in this big long train of spacecraft, and they slowly drift apart over time. But around the early days, they're very close together, and you don't know necessarily which is yours straight away. I mentioned that the space track, they track all the spacecraft and release the models for them, but they only release them about 3 to 4 days after the spacecraft had been launched, or it could be weeks sometimes. So often the early days, you don't even know which spacecraft is yours, where it is. So we have quite a hard job of trying to find spacecraft sometimes and determine, is this even the spacecraft we're looking for? Even if we receive a signal. One way we can do that, though, is with something called Doppler shift. So this is like the classic example, if you have an ambulance drives past you, or it can just be a car driving past at a constant velocity. It will sound like when it's coming towards you, it's a higher pitch, and as it goes past you, it's a lower pitch. So it's the classic, whoa, 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 whoa. I'm sure all of you have experienced that at one point in time. After. Yes, so a Doppler shift is the same for spacecraft. So that's the example. The ambulance is in the audio domain. So that's when you're listening to sound waves, but happens in the light domain as well. It happens to radio signals, which is very convenient because if we know roughly where a spacecraft is supposed to be, we can listen to a signal. If we can hear a signal as the spacecraft comes over, we can look at the Doppler shift that we're actually hearing in the signal and compare it to what we'd expect. And if it's wildly different, then it's probably the wrong spacecraft we're looking at. There are other various research topics that we are undergoing at the moment. One of them is into actually locating and tracking the spacecraft ourselves using the signals we receive. So the US military use radar. A lot of people use radar to actively track spacecraft or space debris. We are looking at just using the signals we're receiving from the spacecraft to build up a model of where they are. And again, if we have multiple sites on Earth, it's kind of like GPS, except in reverse. So on Earth, we know where all of our ground stations are, and the spacecraft is moving. Typically, the GPS is the other way around. The spacecraft are all moving, and you're on Earth, and you're trying to figure out where you are. And the GPS receiver on your phone, for example, will listen to all the GPS satellites coming over, and it has very accurate timing of those, and it compares the time that it receives all the signals from the different spacecraft, and it knows where those spacecraft are, and from that it can triangulate where you are on Earth. We're trying to do that in reverse, so we know where all the ground stations are, and we're listening to a spacecraft going over, and we can hear the difference in when each of the ground stations receives the signal from the spacecraft, and then we can use that to triangulate that a spacecraft is in space. So that's just one of the other research projects that we're doing. Obviously, we use NumPy and SciPy, as I mentioned earlier, to do a lot of that number processing and computation, and then we use Matplotlib to visualize the result. So just to step a little bit more into actually the sciencey side of things. It's not getting too boring. I know it is getting a bit late in the day for this probably, but basically, if you have a guitar, for example, and a guitar has 6 strings, let's pretend it's only got 3. So we play each of those 3 strings, they have a different pitch, they have a different frequency. If we play them all at the same time, we essentially add up those 3 frequencies, and it becomes an entirely different sound again. So this is known as a chord, right? Anyone who is an avid music player will know about chords. Now, what would be really useful is if we can actually turn this around. So for spacecraft, because there's lots of spacecraft going over, they're all using a different frequency to talk at the same time, we get some jumbled up signal. But we want to know, what is this spacecraft on this frequency doing? It'd be really, really cool if we could do that, if we could split all these signals up into the different components of the different frequency components. And it turns out we can do that. So we can use what's called a Fourier transform. Anyone who's done signal processing, I'm sure, will know all about Fourier transforms. They're basically a mathematical tool that allows you to take a given signal and break it up into its constituent frequencies. So if I take the Fourier transform of this red signal here at the top, it looks something like this. And we can see that we have a peak at 1 Hertz, a peak at 0.5 Hertz, and a peak at 0.3 Hertz. And they correspond almost perfectly with the constituent frequencies that made up the original waveform. So this is good. This is really, really good. This is exactly what we want. But real signals they're not consistent in time. They change over time. So what happens if you add up 3 signals that are all changing in amplitude over time, well, you get a Fourier transform like that. Again, we can see there's peaks at roughly 1 hertz, 0.5 hertz, and 0.3 hertz, but there's this weird peaky thing going on. Just doesn't look good at all. So what's the problem there? Basically, we're trying to take the Fourier transform of the entire signal at once. But because it's changing over time, it's changing throughout the signal, we just get this weird mix. The Fourier transform doesn't really know what's going on. So what we need to do is to break up the signal and do a Fourier transform in each subsection. And if we do that, we get 4 different results. So now we can sort of see how the signal characteristics vary over time. Okay, cool. Why is this important? Well, I'm getting to that. But as we can see, the top one we can quite clearly see that we've got 2 frequencies, the 1 hertz and 0.3 hertz. The second one, we can see we've got a 0.5 hertz signal almost exclusively, and you can see that you have in the middle of that second frequency, second red signal, you've got a nice smooth sine wave. So you can see that the results are looking good. But now if we take those frequencies, the frequency powers in the blue, and we plot those on a 2D plot, and we take the amplitude as a magnitude, plot it as a color, we get something that looks like this. So we get a heat map. This heat map is really, 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 really useful to us. So this is actually taken from a real recording from our site, and we can infer a lot of different bits of information from this. We can see here there's a straight line that's a constant frequency. You can see it's not changing in the frequency axis, it's only changing it's only straight in the time axis. So that is a terrestrial signal that's coming from some weird transmitter somewhere that's just outputting a constant frequency tone. Then we've got, of final interest to us is this weird curvy line here. This is a spacecraft. We know it's a spacecraft because we can see the Doppler shift. We can see it changing in frequency over time, going from a high frequency down to low frequency. But it's not the spacecraft we're looking for. How do we know that? Because we know the approximate Doppler shift of the spacecraft we're looking for, and we can compare it to the Doppler shift of this received signal, and it is different. Where would we expect the Doppler shift to be of the received signal? Right about here. And actually, if you look really closely, you can see there's a series of dots up there. They're a bit hard to see because the spacecraft transmitter is bursting. It's only transmitting once every minute or so, or every few seconds rather. So it's a bit hard to see, but it is there. And if you look closely, you can see the Doppler shift we'd expect. We can also see, if you look really, really, really closely, another series of dots that go in the opposite direction. So that is our transmitter. So we're transmitting. When we transmit, we have to correct for the Doppler frequency, the Doppler shift, because the spacecraft also sees Doppler shift from us. As everything is relative, Einstein tells us that. So the spacecraft doesn't want to have to correct for Doppler shift itself, so we correct for it from the ground. Finally, we can also infer that there's actually some wideband noise in our system. This is like if you go to bed at night and you listen to a white noise machine, it blocks out all of the surrounding noise. This is the same for us, except we want to hear the noise. We want to hear the signals from spacecraft. So this is not good. We know that there's something in the near area that's outputting a whole bunch of noise, and we want to find out where it is. So from this, we can infer lots of different information just from plotting this graph in a logical manner like this. So to summarize, we use Python because it's fantastic for high-level data processing, but it's not quite so good perhaps for other areas. So we use it where it's useful. It also provides really good modularity, which allows us to have lots of different systems all play together very nicely. It has a fantastic community support, unbelievably great. And that's thanks to a lot of people like yourselves who, in their spare time, write open source libraries. And we use the GNU radio framework to help us very easily and quickly develop radio systems to download, receive, and process data. And thanks to all this, we can use Python across all of our operations, everywhere from controlling our antennas right to receiving and processing the data. Thank you all for listening. I don't know if I've got time for questions, but I will be here, like I say, all weekend.